Our next set of videos are going to focus on discussing the greenhouse effect and eventually climate change. So to begin the study of the greenhouse effect, we really need to focus on radiation and the history of radiation, really. The first person to really advance its study was Max Planck, when he was just looking at objects that were heated up and the radiation that they would emit. We're familiar with the idea that if something gets very, very hot, it will turn red, and after it continues to warm up, it'll eventually turn white, and if you really get it really hot, eventually blue. This concept is what's known as Blackbody Radiation. We'll describe it a little bit more in a bit here. But Max Planck was the main guy led the research on this in terms of connecting it to quantum mechanics. But we got a couple of guys, Stefan-Boltzmann, who helped to come up with an empirical relationship that explained it in terms of thermodynamics in a general sense. So the whole idea here, right, is that all bodies that have a temperature, whatever the temperature is, are going to radiate energy as electromagnetic radiation, as we studied photons, right? And that this radiation we typically consider, all right, to be the Blackbody radiation. Blackbody radiation is specifically when we have radiation coming from a perfect absorber or emitter of radiation. But all objects emit, multiple parts of the spectrum, but based on their temperature, they're going to only be focused in certain areas. So what happened here, all right, is what you think of is a shiny versus like a dull metal can. Okay, like if you have a shiny metal can, it's going to be very good at any light-colored or silvery object can be very good at reflecting radiation. But dark objects and one that might be painted black, all right, would be a very good emitter or absorber of electromagnetic radiation. All right, so this was first studied just by taking a porcelain sphere, filling the inside with soot, all right, and then heating it to high temperatures and being able to see the colors that would come from it. And that was the way we studied blackbodies. And the idea with this having a cylinder, or excuse me, a porcelain sphere, was such that if you only had a small hole, any radiation that would be coming in from the outside would definitely be absorbed if it were reflected at all. And so what you would see coming out would be the radiation created by the temperature that the porcelain was heated to. All right. So we have here, okay, emission spectra effectively is what's happening. All right. As the porcelain gets hotter and hotter, we see colors going from, like I said before, red, yellow to blue, and actually between yellow and blue it would be white. All right. And what we can see, all right, we can actually graph the intensity of all the different wavelengths of light, and we get this little distribution. Okay, so not all wavelengths are going to be emitted with equal intensity. In fact, since they all have different intensities, we can graph this. All right, that wavelength that has the highest amount of intensity, we'll call it lambda max. That's going to be directly related to the temperature. Okay, so lambda max. It's directly related to the temperature of the substance. And what we see here is that we have this intensity that's being emitted, and the power we graph the power density, okay, on the y-axis and the wavelength on the x. And if we actually take the integral of this whole thing, the area underneath the curve, all right, is going to be directly proportional to the intensity of the electromagnetic radiation that's emitted. Okay. What we see here for these different temperatures, all right, the curve keeps growing, and we see a couple of features that are really interesting. All right, as the body heats up, we start here with this graph here. We have a 1250 Kelvin all the way to 2000 Kelvin, and then the graph to the right, all right, the line for 2000 Kelvin can't be seen, but we work our way up from 3000 all the way up to 6000. There's two things that happen. As the temperature goes up, the maximum wavelength is going to decrease. Okay. So let me write this again here, okay? As the temperature goes up, lambda max will go down, all right? And this makes sense since lambda, all right, this is going to be inversely proportional to the frequency, all right? So this basically means that frequency goes up, right? Or the maximum energy of the photons will be going up, right? So this is getting at the idea here that why we go from red all the way to blue when we're seeing the temperature go up is the wavelength is decreasing. And what ends up happening with the total power, all right, total power or intensity, however you want to refer to it, as temperature increases, you have this. As temperature increases over here, the total power increases as well, okay? So we see this relationship, all right, where lambda max is inversely proportional to the temperature. And this is what we're going to describe as Wien's law, okay? So Wien's law is just this relationship. It's an approximation, all right? And it looks like this. And it helps us to see what the peak wavelength of the object will be based on its temperature. Okay? So if you wanted to, you could draw on here, all right, on this set of axes, two emission spectra, all right, one radiating at a low and then another at a high temperature, and then you can label which curve belongs to which temperature here, all right? So if you were to draw this, it looks something like this, I suppose. I'll draw this one like this, and then this one like this. All right, and here, this is wavelength on the x-axis. Power density is what we're going to call this on the x-axis. Okay, and so this is the higher temperature curve, and over here we have our lower temperature curve. Okay. All right. So that's pretty much it. Okay, for what we need to know about blackbody radiation. Okay, just perfect absorber or emitter of radiation. Gets at that idea of wearing a black T-shirt on a day where the sun's out. Right, you're going to feel a lot warmer than you would feel wearing a white T-shirt. Okay, you're absorbing all that electromagnetic radiation. Okay, let's see here. The sun, actually, all right, I don't have this in the notes, but just something extra here I want you to know. The sun we consider to be a blackbody radiator. Okay. The surface of the sun is approximately 6,000 Kelvin, all right? And we see that it has a peak wavelength of 500 nanometers. So the sun appears to us as a yellowish white. That's where the peak would be for 500 nanometers, all right? So the light that we end up receiving from the sun because of this, since it's a blackbody at 6,000 degrees Kelvin, it's split up into these percentages in terms of the areas of the spectrum that it occupies, all right? Now, it is important to mention at this point that there are some lines that are missing in terms of absorption spectra, okay? But the rest of the shape of the curve does match up very close to that of a blackbody at 6,000 Kelvin, all right? All right, so those absorption spectra deal with the hydrogen lines, the hydrogen that's in the sun, all right? Okay, so now, just a few things to define. This is stuff you know, but just to review it, okay? Dealing with power here, it's energy divided by time, units being watt or joule per second, okay? And then power over area is intensity, and this is going to be watt per meter squared, all right? So we've been dealing a lot with that, so that shouldn't be anything new, all right? New relationship though here, the Stefan-Boltzmann Law of Radiation. This is what I told you. They came up with this relationship to approximate the intensity as it's related to temperature. And what we see, okay, if you look at the power, actually, it's directly proportional to the temperature to the fourth power. All right, there's their constant proportionality in that relationship. And really, you can just look at this as the intensity is equal to the Stefan-Boltzmann constant times temperature to the fourth power. That's the empirical relationship that they came up with. Okay. So that's the law that you need to have there, as well as the constant, the Stefan-Boltzmann constant. And that, by the way, is a lowercase sigma, in case you're wondering what it is, as far as the symbol. All right, so let's just do some practice here, all right? We got our supergiant star Betelgeuse. It has a surface temperature of 2,900 Kelvin, all right, which would be in the red part of the spectrum. So determine how much energy Betelgeuse and it has that radius there too. So we want to know how much energy it radiates each second, if we can assume it to be a black body. All right. So effectively, that's asking for the power. So what is the power equal to? And we have the Stefan-Boltzmann relationship here with area here on the right side of the equation. And what we're looking at here is an object, it is a surface area over which the object emits electromagnetic radiation. And we can assume that Betelgeuse is a sphere, so we're going to be calculating this as the surface area of a sphere, which we know is 4 pi r squared from geometry. All right. The temperature here is 2900 Kelvin. We're going to use this as our radius right here. All right. We know the Stefan-Boltzmann constant, so we can plug all this stuff in and calculate it. All right. So it's going to be equal to the 5.67 times 10 to the negative 8 watts per meter squared per Kelvin to the 4th power. All right. This is going to be times, let's see here, 4 times pi times 3 times 10 to the 11th meters. Oops. There we go. Squared. And this times the temperature, which is 2900 Kelvin. And that's to the 4th power. All right, that's the relationship that they came up with. And what we see here is that this star radiates energy at a rate of 4.5 times 10 to the 30th watts. It's a lot of energy right there. All right. So what is the intensity of the energy radiated by Betelgeuse? Well, we're going to take this and we're going to divide it by that area. All right. So we want intensity. It's going to be equal to power divided by area. And so it's going to be 4.5 times 10 to the 30th watts divided by 1.13 times 10 to the 24th meters squared. And we calculate this, we end up with about 4.0 times 10 to the 6th watts per meter squared. All right. So the question is, how will the power radiated by Betelgeuse change, okay, if the temperature doubles? So be aware here, right? If the temperature doubles, okay, this whole thing's to the 4th power, right? So what this ends up being is 16 times the original power to that 4th, okay? So just another little IB style question there for you. Okay. All right, moving on here. Some more practice, okay? Right here, it's the, we're talking about the intensity, okay, of the energy radiated by the Earth. We have that right there, and we can assume it to be a black body. So we want to calculate surface temperature based on this relationship, all right? So we know intensity is going to be equal to 388 watts per meter squared, all right? We want to know what temperature is. So we're just going to use the Stefan-Boltzmann relationship. All right, there we go. Solving for the temperature is just going to be the 4th root with the intensity divided by the Stefan-Boltzmann constant. And there we go. Substitute all this business in here. And we end up with this, 288 Kelvin. Okay. Now this is just a sloppy little calculation that we're doing here, and it turns out you don't need the radius at this exact moment, but later on we'll need it for doing other calculations. All right. So that's it for this video, and the next video we're going to talk about emissivity and some other radiation problems and albedo as well.